Today we'll discuss about the catalyst. Potassium chloride, when heated, strongly decompose, slowly giving dioxygens. So the decomposition occurs at the temperature range of 653 to 873 Kelvin. So however, a little of manganese dioxide is added, then the decompositions take place at a considerably lower temperature range, that is 473 to 633 kelvins, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to the mass and compositions in a similar manner. The rate of a number of chemical reactions can be altered by the presence of foreign substances. That means this is nothing. When we added manganese dioxide as a catalyst during the decomposition of potassium chloride, the rate of the reactions become faster. This rate of the reactions become faster because of the decrease in the activation energy. So that means the temperature which we require for the decomposition gradually decreases till up to 653 to 873. Now this temperature gradually decreased down up to 473 to 633 kelvins. So here we know that the presence of catalyst gradually increased the rate of the reaction or decrease the rate of the reaction. That depends on the type of the catalyst. As we know that positive catalysts are those catalysts which accelerate the rate, whereas negative catalysts are those catalysts which retard the rate of the reactions. So in case of positive catalysts, say the positive catalysts work to decrease the activation energy, whereas negative catalysts that increase the activation energy of the reactions, thereby rate gradually decreases. So the systematic studies about the effect of these substances, that means this catalyst, on the rate of the chemical reaction was first done by the scientist called Berzelius in the year 1835, and he gave this foreign substance which retard or which increase the rate of the reaction as a catalyst. So the word catalyst was coined by Berzelius in the year 1835. Substances which alter the rate of the chemical reaction and themselves remains chemically and quantitatively unchanged after the reaction is known as a catalyst. So this is the definition of the catalyst. So a catalyst is the substance which alter the rate of chemical reaction and themselves remains chemically and quantitatively unchanged after the reactions. So the phenomenon is known as a catalysis. So the phenomenon to keep the particle itself unchanged and alter the rate of the reactions, that we call as a catalysis. So here we have already know that there are some substances which increase the rate of the reaction, there are some substances which decrease the rate of the reaction. So those substances which enhance the activity of the catalyst, means which increase the capacity of the catalyst, while poisons decreases the activity of the catalyst. So here we know that those chemicals in which it increase the rate of the reaction, that we call as a catalytic promoters, whereas those catalysts which decrease the reactivity of the rate of the reactions, that we call as a poisonous catalyst. So in Harvard process for manufacturing ammonia, molybdenum act as a promoter. So for irons, so during the here let us see the equations. N2 plus 3 times of H2, we use iron and molybdenum, so that you will get it ammonia gas. Here the iron is a catalyst and molybdenum is a promoter of that. So the function of that catalytic function of the iron is increased due to the presence of molybdenum. So such a substances we call as a promoter. So based on the nature, we can classify a catalyst into two types. That is, first one is homogeneous catalyst and another one is heterogeneous catalyst. As we know that homo means equal, so when the reactant and the catalyst are in the same phase, then the process is said to be homogeneous catalyst. So that means the reactant state and the product state and the catalyst state should be always equal, then it is called as a homogeneous catalyst. So let us see one example of that. Oxidation of sulfur dioxide into sulfur trioxide with dioxygen in presence of oxides of nitrogen as a catalyst in the lead chamber process. So SO2 plus O2 gives twice SO3 during the time we use a catalyst. NO act as a catalyst. So here the catalyst is of gases, sulfur dioxide is also gases, oxygen is also gases, and the product SO3 is also gases. So all the reactants phases and the product phases are of same. So it is of homogeneous catalyst. In case of hydrolysis of methyl acetate, here your ice plus ion furnished by the hydrochloric acid. So in case of hydrolysis of methyl acetate is catalyzed by acid. So here methyl acetate is a liquid, water is also liquid. Hydrolysis means addition of water is called as hydrolysis. So during this reactants are your methyl acetate and water, which are of liquids. Even your catalyst, that is ICl, is also taken as a acid. While we undergo hydrolysis, we get an acid and an alcohols. So all these are of in the liquid state only. So that means the product are also liquid, the reactant are also liquid, and the catalyst also liquid. So it is of homogeneous catalyst. Like this one, we have different examples. Hydrolysis of sugar is catalyzed by acid, and there is sulfuric acid. So here sulfuric acid is liquid, your sugar solution is also liquid, in water is also liquid, which act as a reactant, and your sulfuric acid act as a catalyst here. The product is glucose and the fructose, which are also found in the aqueous state. So there is in the liquid state. So all the reactants and product and catalyst are of same phase. So it is an example of homogeneous catalyst. Now heterogeneous catalyst is opposite of the homogeneous catalyst, means the reactant, the product and the catalyst are in different state. Then it is called as a heterogeneous catalyst. Let us see one example. Oxidation of sulfur dioxide into sulfur trioxide in presence of platinum. Here it was SO3. Now we use the catalyst platinum and then we got sulfur trioxide. Here sulfur dioxide and sulfur trioxide are the reactants and product which are of gases, whereas platinum is a solid. So your catalyst is a, now the catalysts have different state as compared to your reactant or products. Thus it is of heterogeneous catalyst. Now next example for this is combination of dinitrogen and dihydrogen to give ammonia. During the Haber process we use iron. So here iron is a solid and nitrogen and hydrogen which are of reactants are of gases, and the product ammonia is also gases. So it is different. That means the state of the catalyst is different from the state of the reactant or state of the products. Thus it is of heterogeneous catalyst. Like this one, during the oxidation of ammonia into nitric acid in presence of platinum gas in Oswald process. So 4 times of NH3 plus 5 times of O2. Then here we use platinum. Then we got 4 times of NO and 6 times of H2O. Here ammonia is also gases, oxygen is also gases, and the product, that means nitrous oxide and water are of gases. And means reactant and product are gases, but the catalyst platinum is of solid. So this is a heterogeneous catalyst. During the hydrogenation of vegetable oil in presence of finely divided nickels, in presence of nickel as a catalyst, then vegetable oil plus hydrogen, then in presence of nickel we get vegetable ghee. Here your reactants, that is vegetable oil, is of liquid, hydrogen is a gas, nickel is a solid, and then vegetable ghee is of solid. That means here the reactants have different in state as compared to the your catalyst. So it belongs to your heterogeneous catalyst. So this is what about the types of the catalyst. Now we will see absorption theory of heterogeneous catalyst. That means how absorption takes place in the heterogeneous catalyst we need to discuss here. And this theory explains the mechanism of heterogeneous catalyst. The old theory, that is absorption theory of catalyst, was that the reactant in gaseous state or in solution state are absorbed on the surface of the solid catalyst. The increase in the concentration of the reactant on the surface increases the rate of the reaction. So absorption being as an exothermic process, the heat of absorption is utilized in enhancing the rate of the reaction. The catalyst action can be explained in terms of the intermediate compound formula. So the theory of which we have already discussed. That means first the reactant molecule absorb on the surface of the catalyst, and then it start formation of the intermediate compounds. When the bond completely form between the reactant molecules, then it goes into the product by leaving the catalytic surface for the further reactions. Like this one, the catalyst, a small amount of the catalyst can accelerate a huge amount of the reaction. So during the catalytic reaction we have first work is absorption of the reactant molecule. Second one is this, it gives the surface area for combining the reactant molecules. After then formation of intermediate compounds, then after completing this step, then desorption from the surface of the catalyst. This is what the work of a catalyst. In the modern absorption theory, this theory is the combination of intermediate compound formation theory and old theory of absorptions. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. First one, diffusion of the reactant to the surface of the catalyst. First, diffusion takes place on the surface of the catalyst. Diffusion means intermixing. Now, absorption of the reactant molecule on the surface of the catalyst. Next is occurrence of chemical reaction on the catalytic surface through the formation of the intermediate. Next step is desorption of the reactions, desorption of reaction product from the catalytic surface, thereby making the surface available again for more reactions to occur. The last step is diffusion of the reaction product away from the catalytic surface. So the surface of the catalyst, unlike the inert pair of the bulk, has free valences which provide the seat for chemical forces of attraction. A gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If different molecules are absorbed side by side, they may react with each other, resulting in the formation of the new molecules. Thus, foam molecules may evaporate, leaving the surface of the fresh reactant molecules. That means the catalytic reactions occurs completely by using 5 steps. The first step is what we have discussed, is that diffusion of the reactant. Then reactant molecule comes on the surface of the this catalyst and start intermixing. Second one is absorption of the reactant molecule on the surface of the catalyst. Third step is occurrence of chemical reaction on the catalytic surface, means formation of intermediate compounds start in the third step. And the fourth step is desorption from the surface of the catalyst. The desorption of the product from the surface of the catalyst is the next. After desorption, then the product molecules need to move from the surface of the catalyst away, and that gives the space for the further reactions. How it gives away from the surface is we have already discussed here. That means the surface of the catalyst has free valencies. Remember, the surface of the catalyst has free valencies. So these valencies are provided to make a chemical force of attractions. So if any substances which can work as a catalyst, that means they will have always free valencies. Then only they can behave as a catalyst. So here we can ask why d block elements have catalytic properties. So in the d block elements we have free, means that unpaired d orbital electrons which allow them catalytic properties. This theory explain, that means this absorption theory explain why a catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective even in the small quantities. So although if you have taken the small amount of the catalyst, it can catalyze a huge amount of the reaction, because catalytic surface is used. The substance which a catalyst are not directly involved in the chemical reaction. Now let us see important features of solid catalyst. Important features of solid catalyst. The first one is activity. The activity of a catalyst depends upon the strength of the chemoabsorption to a large extent. That means the work of a catalyst depends on the strength to form chemical bond. The reactant must absorb reasonably strong on the catalyst to become active. However, they must not get absorbed so strongly that they are immobilized and other reactants are left with no space on the catalytic surface for absorption. It has been found that hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with the maximum activity being shown by group 7 to 9 elements of the periodic table. That means the catalytic activity is maximum if we use the elements which is from group 7 to group 9. Why? Means that because it has maximum free electrons in the d orbitals. Generally, group 5 to group 11 metals always have free valence electron in their d subcells. This makes them higher in catalytic activity. Now, all this shows that the catalytic activity of a reaction depends on the amount of the free electrons remains in the metal. So next is selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product. So every metals cannot act as a catalyst in a particular reaction. That means the catalytic activity is specific. For a particular reaction, a particular elements can be used as a catalyst. So, let us take it one example, H2 plus CO, then we get CH4 plus H2O. Here we use a catalyst nickel, whereas in case of carbon monoxide plus hydrogen to form methanol, we use copper with zinc oxide or chromium oxides as a catalyst. When we combine with carbon monoxide and hydrogen in presence of copper metal, we got acetaldehyde. So this shows that different reactions can have different catalysts. That means the catalytic activity is different. So for a chemical reaction to act as a catalyst, we need to select the type of the catalyst which may be possible to act as a catalytic work. So selectivity is important. Thus, it can be inferred that the actions of a catalyst is highly selective in nature. A given substance can act as a catalyst only for a particular reaction, not for all reactions. That means substance which act as a catalyst is in one reaction may fail to catalyze the another reaction. Catalytic reactions that depends upon the pore structures of the catalyst and size of the reactant and product molecules are called as a shape-selective catalyst. What is shape-selective catalyst was already in the board exam. You must remember that. Shape, that means those catalysts which work depends on the shape, as well as you need to select for a particular reactions. That is what we call as a shape-selective catalyst. So again we can discuss it. Catalytic reactions that depends upon the pore structures of the catalyst and size of the reactant and product molecule. If the catalytic works, the reactions depends on the structure of the catalyst as well as size of the reactant and product, then the catalyst is called as a shape-selective catalyst. Example is zeolite. Zeolite means that porous structure. Zeolite have porous structures like honeycomb. So because of porosity, it will have higher in the surface area. So it can easily use as a catalyst. So this is an example of shape-selective catalyst. This zeolite is generally contain aluminosilicate with three-dimensional network structures of silicate in which some silicon atoms are replaced by aluminum atoms, giving ALOSI framework. The reaction taking place in zeolite depends upon the size and shape of the reactant and the product molecule as well as upon the pores and cavity of the zeolite. And they are found in nature as well as synthetic for catalytic activities. Zeolite are being very widely used as a catalyst in petrochemical industries for cracking of hydrocarbons. Cracking means breaking down of bigger hydrocarbon into smaller hydrocarbons with the production of one alkenes, that we call as a cracking. So cracking of hydrocarbons. During that cracking of hydrocarbon we use zeolite. An important zeolite catalyst used in the petroleum industries is ZSM5. It converts alcohol directly into gasoline by dehydrating them. Dehydrating means removing water to give a mixture of hydrocarbons. Now let us see enzyme catalysts. Enzymes are a complex nitrogenous compound which are produced by living plants and animals. So we know that enzymes are the biological catalysts which contain nitrogen. Enzymes are the biological catalysts which contain nitrogen. They are actually protein molecules. Generally enzymes are nothing, protein molecules of higher molecular mass and form colloidal solution in water. They are very effective catalysts. Catalyze numerous reactions, especially those connected with natural process. Numerous reactions that occurs in the body of the animals and plants to maintain the life process are catalyzed by the enzyme. The enzymes are thus termed as a biochemical catalyst, and the phenomenon is called as a biochemical catalysis. Many enzymes has been obtained in the pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. Let us see some enzyme catalyzed reaction. Inversion of cane sugar. That means during this inversion of cane sugar into glucose and fructose, it was catalyzed by enzyme invertase. Like this one, conversion of glucose into ethyl alcohol was catalyzed by zymase, enzyme zymase. So glucose, when it was catalyzed by enzyme zymase, then ethanol and carbon dioxide, ethanol and the carbon monoxide you will get it. The conversion of starch to maltose was catalyzed by maltase. So always remember that in the carbohydrate OSE will be used as a suffix, whereas in case of enzyme you need to use ASE. So conversion of maltose to glucose was catalyzed by enzyme maltase. So let us see that example. C12H22O11 plus H2O, then maltase, then you will get it 2 times of C6H12O6. Now next is decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzed this decomposition. So urea plus water, then which was catalyzed by urease, then you will get ammonia and the carbon dioxide. In stomach, the pepsin enzyme convert protein into peptide, while in intestine, the pancreatic trypsin convert the protein into amino acid by hydrolysis. So always remember, in stomach, pepsin convert proteins to peptide, while in intestine, pancreatic trypsins convert protein into amino acid by hydrolysis. Now conversion of milk into curd. During this process, the lactobacillus enzyme convert milk into curd. Now let us see some enzyme reactions. Enzyme invertase presence in yeast convert sucrose to glucose and the fructose. Now enzyme zymase presence in yeast convert glucose to ethyl alcohol and the carbon dioxide. Enzyme diastase obtained from malt convert starch to maltose, and then enzyme maltase found from yeast convert maltose to glucose. Enzyme urease found in the soybean convert urea to ammonia and carbon dioxide. Enzyme pepsin present in the stomach convert protein to amino acid. Now let us see about the characteristics of enzyme catalyst. This characteristic of enzyme catalyst is very important for the exam again. Enzyme catalyst is unique in its efficiency and higher degree of specificity. Means that particular reactions can be catalyzed by only one enzymes, and a small amount of the enzymes can catalyze a huge amount of the reaction. So we can conclude the enzyme characteristic as number one, most highly efficient. One molecule of an enzyme may transform 1 millions of molecules of reactant per minute. Now highly specific in nature. Each enzyme is specific for a given reaction, that is, one catalyst cannot catalyze more than one reaction. Now highly active under optimum temperature. The rate of an enzyme reaction become maximum at a definite temperature. The temperature is called as a optimum temperature. So what is optimum temperature? We can ask. Optimum temperature is the maximum temperature in which an enzyme can work in its highest capacity. So on either side of this maximum temperature, the enzyme activity decrease. The optimum temperature range for enzyme activity is 298 to 310 Kelvin. Human body temperatures being 310 is suited for enzyme catalyzed reaction. So this is the reason for why when you suffer fever, during the time you never feel hungry, because our food was digested by enzyme catalyzed reactions. But if you have fever, then your body temperature is more than optimum temperature, thereby enzyme activity decreases, and hence you never feel hungry. Now next is highly active under optimum pH. The rate of enzyme catalyzed reaction is maximum at a particular pH called optimum pH. So optimum pH means the pH of an substance in which the enzyme activity is maximum, that we call as a optimum pH. So optimum pH in our body is 5 to 7. Now increasing activity in presence of activator and coenzymes. The enzymatic activity is increased in presence of certain chemicals. Those chemicals which increase the enzyme activity is called as a coenzyme. Coenzymes are generally your carbohydrates or non-proteinous material. So non-protein, that is vitamins, this and that. When a small non-protein vitamins, within bracket vitamins, is present along with an enzyme, the catalytic activity is enhanced, means that the catalytic activity is increased. That is why when you have sick, the doctor give some vitamins along with your prescribed medicine. So these vitamins help to absorb the medicine in your body easily. That's why doctor always prescribe vitamins. So activators are generally metal ions. Here enzyme activators are generally metal ions such as sodium, manganese, copper, cobalt. The metal ions when weakly bonded to the enzyme molecules increase their catalytic activity. Amylase in presence of sodium chloride. Sodium ions are catalytically very active. So like this one, we have one is activator, another one is coenzymes. So here we have discussed coenzymes increase the enzyme activity and activators weaken the enzyme molecule, weaken the bond to enzyme molecules, and generally activators are your metal atoms. Now influence of inhibitor and poisoners. Like ordinary catalysts, enzymes are also inhibited or poisonous by presence of certain substance. The inhibitors or poisonous interact with the active functional group on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzyme. The use of many drugs related to their actions as enzyme inhibitor in the body. So enzyme inhibitor means those substances which inhibit or which decrease the activity of the enzyme. That is what you call as a enzyme inhibitor. So generally this enzyme inhibitor block the active site of the enzymes. Active site means active site generally contain a functional group which can interact with the this enzyme part, which can interact with the others chemical which comes to react with the enzymes. So this, if active site is blocked, then one of the enzyme cannot react with the drugs. It is why the drugs are not work if enzyme inhibitors are there. Now mechanism of enzyme catalyst reaction. This one we already discussed about Logan Key Theory. So in the Logan Key Theory, without key you cannot open a lock. Same thing like this, the enzymes have an active site. On that active site, the functional group presence on that can need to able to react with the incoming substances so that it can easily catalyze the chemical reaction. So let us see it again based on your book. There are number of cavities present on the surface of the colloidal particles of enzyme. The cavities are of characteristic shapes and possess active groups such as amino group, acid group, then hydroxyl group, then SS group. They are actually the active center of the surface of the enzyme particles. The molecule of the reactant, which molecule of the reactant we call as a substrate. So which have complementary shape and fit into these cavities just like key fit into the lock. That means the shape of the enzyme, the shape of the incoming group and the holes of the active site shape should be always equal. Then only these enzymes can catalyze the chemical reactions. On account of presence of the active group, on account of the presence of active group, an activated complex is formed when they decompose to give the products. Thus, enzyme catalyzed reaction may be considered to proceed into two steps. First one, binding of enzyme with the substrate. Substrate means non-porous material. So enzyme plus substrate gives enzyme substrate, which is a activated complex. So next is one of decomposition of the activated complex to form the product. So ES when decomposed, then you get E and the P. This is the overall enzyme catalyzed reactions mechanism. So here are some industrial catalytic process. As we already discussed, we will not discuss on this. And for this part, we'll discuss up to this enzyme activity. Thank you.